Well, just to give you a little background on myself, um, I came to Goddard in 1997 as a contractor, just a couple years after my getting my PhD at Washington. Became a civil servant in '98, so I've been there about 27 years now. Hoping to continue that for a while, if all depending on what happens in the near future. But enough of that. Let me go ahead and uh, get started with this. So, thank you for joining. I'll talk about the way I like to think of it is hurricane hunting, NASA style. We'll talk a little bit about hurricane hunting and then what NASA does in studying hurricanes. And just for the sake of being safe, the contents of the presentation are mine personally and don't necessarily reflect any position of NASA. And the main reason I say that is because I'll talk a little bit about the impacts of climate change at the end of the talk. So let's talk about what hurricane hunting is. So most you know during hurricane season, you probably hear about the Hurricane Hunter aircraft doing reconnaissance within storms. They've been doing this since around the time of World War II. In fact, the first aircraft flight through a hurricane was supposedly based on a dare. Um, and in the end, they determined that it was actually quite useful to collect information on storms this way. So the video you're seeing is from a NOAA P-3 aircraft flying into a major hurricane. As they fly into the eye of the storm, you can see that stadium effect once being surrounded by the eye wall. Typically, when they're flying these storms, they tend to do these repeated figure four patterns to try to get information in all quadrants of the storm. And they want to do that repeatedly to be able to look at how things are changing with time. And then that information uh, goes to the forecasters. They use that subjectively to as part of all the information they consider in determining their forecast. But increasingly, that data is also used in the numerical weather prediction models to improve the actual weather forecast from those forecast models, and that helps contribute to these track forecasts. I think since a major investment after Hurricane Katrina in 2005. Um, there was a big program called the Hurricane Forecast Intensity Program, funded for NOAA, that has actually improved track forecasts and intensity forecasts by sort of in the range of 30 to 50%. So substantial improvements over that time because of those investments. These are some of the aircraft that are used for hurricane hunting. There's two different NOAA aircraft. There's the NOAA P-3 Orion. There's actually two of those. They're nicknamed Kermit and Miss Piggy. They have on them a radar on the belly that helps to map out the horizontal precipitation structure. And then in the tail of the aircraft, you see this protrusion out in the tail. There's a radar, a Doppler radar there that maps out the three-dimensional wind and precipitation field within the storm. They also release dropsondes, which are small packages that fall from the aircraft and get profiles as they descend to the surface. And they have some other instruments as well. NOAA, and that's the one that penetrates the storms, the eye wall of the storm. The NOAA G4 is a high altitude aircraft. It cannot penetrate the core of the storm generally, so they tend to fly very close, but outside of the storm, and even do broad surveys of the environment. And the data that they collect, including dropsondes and radar measurements, are also used to look at the structure of the storm, but also how it's interacting with the environment and how that determines the motion of the storm. And then there's the Air Force flights on C-130 aircraft. They have, I think, at least two of these aircraft, maybe more, that do regular penetrations, collecting flight level winds and dropsondes and some other data sets. And all these data are used in real time to monitor the change in intensity of the storm, the structure of the storm, and then feed these forecast models. So their main purpose is in aiding operational forecasting. That means that it goes into the models and it's what leads specifically to actionable forecasts and warnings for communities. NASA takes a different approach. I like to say we do hurricane hunting, but it's for a different purpose. So we do we collect observations both from space and from aircraft to improve basic understanding of hurricanes, how they form, what their precipitation structure is globally, and the processes that lead to the intensification of storms. We have a number of different satellites that provide information on the environment of the storm, the ocean temperatures that provide energy, and also look at the impacts of these storms. So, total rainfall accumulation, where power outages are occurring, where standing water might be located that could, in some areas, lead to mosquito borne diseases, and look at flood and landslide. So, we have a number of applications that our satellite observations feed into. One of the key activities for NASA is developing new measurement technologies. We often do these initially for measurements on the ground or from aircraft. And then for appropriate measurements, we will eventually transition some of those to space. And even though what you often see in the news is NOAA's operational satellite data, those are actually built at NASA, both their geostationary and many of their polar orbiting low Earth orbit satellites are built at NASA. We launch them and then we hand them over to NOAA for operations. So, in today's presentation, I'll kind of cover the basic ingredients of a hurricane, what makes them form, what makes them intensify. I'll talk about some of the observations, not all of them. We don't have enough time, but at least some key ones. We've done a number of airborne science campaigns over the year. You're seeing in the animation some of the data collected from a large unmanned aircraft from flights. I think that one was from 2014. And then we'll look toward the future in terms of the potential impact of climate change and kind of connect that to the basic ingredients that we'll talk about next. So, before we get into this, we got to build a foundation for understanding. So, there's just some real simple things to understand before we get going. So, if you look at these equations, you can see. Oh, wait, no, just kidding. I like to show this. Some people get a laugh out of it, but this is gives you a sense of the complex math that can be behind tropical cyclones. But let's start more basic, and that's with the basic structures within hurricanes. You're probably familiar with a lot of these. Um, the worst part of the storm is the eye wall, where you got the strongest winds within the hurricane and rapidly rising air that leads to the wall of thunderstorms that make up the eye wall. There are two components to this circulation that we typically think of. There is the primary circulation, which is the large rotational flow associated with the storm, as indicated by these green arrows. Um, so, in the northern hemisphere, they're going counterclockwise near the surface, and then as you get to upper levels, you get a dome of high pressure that then tends to have the air moving out from the storm in a clockwise fashion. And then we have what's called a secondary circulation, which is the in, up, and out circulation. So you get radial inflow from the environment in toward the center at low levels, close to the surface. That brings in high momentum air in the environment, and it brings it into the center. And because of conservation of angular momentum, that tends to spin up the storm circulation. That air has to go somewhere as it gets into the center, and it tends to go up in these clouds. Some of it is in these outer rain bands, but a lot of that vertical air motion occurs in the eye wall itself and then moves outward at upper levels. So it's in, up, and out. And these structures have been known for a while through airborne observations and satellite data. And we've learned a lot over the years with those data sets. But two of the most challenging questions that we've had to deal with, and we're still working on these, although I think we have made a lot of progress, is how do storms form and what causes rapid changes in intensity? That question is really important because if you have a storm, say approaching the coast and it's only a Category 1 storm, and if it overnight was to intensify very quickly up to a Category 4 storm, obviously it provides less time for preparedness and evacuation. So we really need to be able to get forecasts of the intensification very accurate so that people have sufficient time to prepare for the storm. So we'll look at those two questions. So the basic ingredients. So probably first and foremost is we need warm ocean temperatures. Of course, you find that typically in the tropics with the ocean temperatures decreasing as you go to higher latitudes. So that's one of the main reasons we see these systems developing in the tropics as opposed to higher latitudes most of the time. You need higher humidity. That allows for cloud formation. If you have dry air in the environment of the storm and that can get into the storm circulation, it can cause evaporation of cloud and precipitation droplets. That evaporation causes cooling, and that cold air can get down toward the surface, and it effectively removes some of the energy for the storm. So it tends to have an inhibiting influence on storm development. You need strong vertical wind shear, and I'll talk a little bit about each of these as we go on here. But that's basically the change in winds with height. If all the winds were in the same direction at the same speed, the storm would just move with those environmental winds. But if they're going in different directions at different speeds, it tends to move the upper and lower parts of the storm in different directions according to those winds, and it can rip storms apart. And we often need background rotation. That means that you need something to work with to start, some initial rotation that then can be concentrated to smaller scales and increased over time. So part of that background rotation just comes from the rotation of the Earth. And if you think about, the Earth is rotating on its axis, so the maximum component of rotation in the vertical is at the poles, and at the equators that goes away because now it's just always pointing out, but there's no rotation relative to, say, a person standing at the equator. So storms do not form at the equator. They form just off the equator where these other conditions are important. Now, there are other sources for rotation that really determine where these storms occur, and they're usually associated with different perturbations in the atmospheric flow. We call them waves. That have concentrated areas of rotation, and those are often connected to distributions of temperature as well as to large-scale thunderstorm systems that can help concentrate rotation in a given area. So I'll show some examples of that in a little bit. Now, although these are necessary ingredients, and we know what these ingredients are, how they come together in any individual storm is not always well understood. Although I will say again, we are improving that knowledge, but we still face significant challenges in observing these different components of the atmosphere and also in modeling them. So let's start with the importance of the ocean temperature. So in general, the intensity that a storm can get up to is a function of how warm the ocean temperatures are. The ocean really is the key source of energy for these storms. And in the meteorological community, we often talk about the maximum potential intensity of a storm. That's how, for a given sea surface temperature, that's how strong a storm can theoretically get, but there's no guarantee it's going to actually get there because that depends on other aspects of the environment. So in this plot, which is showing the maximum potential, the maximum wind speed as a function of sea surface temperature, these different colored lines represent different estimates of the theoretical max. So they increase from about 60 meters per second or about 120 knots at 26 degrees Celsius, which is sort of the minimum temperature typically needed to form a tropical storm. And it goes up to about 85 or so meters per second at the high end, about 30 to 31 degrees Celsius. And each of these little circles represents a storm in the Atlantic. So you can see most of the storms never reach their full potential in terms of intensity. Particularly at these colder temperatures, we see very few. They get close, but not really getting up to that maximum potential. It's not until we get to some of these higher sea surface temperatures that you start to see storms at the extreme end of intensity. So they're reaching that theoretical limit in the most ideal cases. I think you don't see as many at these higher temperatures because it's more of a sampling issue that we don't have very many areas to get to these extreme temperatures, and there may be other effects um, that tend to, we just haven't seen too many at those temperatures to really test that limit. So this is really fundamental to understanding. That's why they occur in the tropics. And you see some of the ocean temperatures that I'll show later. It's also why they're often favored in the Gulf of Mexico and the Caribbean. I mentioned environmental humidity, and this just shows an example of humidity data taken from basically a hodgepodge of satellites that have been merged to form a nice animation. So where you see these warmer temperatures, this is showing the total amount of precipitable water within the column. So it's not really the relative humidity because it reflects the column as a whole. But these orange and red areas indicate regions that have a high amount of moisture throughout the column. You can see in this animation these areas of rotation that correspond to Helene, Isaac, and Florence. This is from 2018. Dry air is indicated by the blue, purple, and the green. So we're able to use satellites to track this information over the ocean basins. And when we see a storm like Helene here, where it's moist all around it, we know at least that it has a good moisture environment for intensification. And the lack of dry air also means that's less likely to be a disruptor for the storm. If you look at Isaac, you can see this dry air that tends to wrap around the storm. Sometimes that dry air can get in to a storm and cause some disruption. But typically that happens most when there's more wind shear, which we'll talk about, I think, next. But this is a great way for us to track the environment of the storms and kind of think about their likelihood of formation. So let's talk about wind shear. As I mentioned before, this is kind of showing the low-level anticyclonic vortex at low levels, and it's clockwise at upper levels, representing low pressure near the surface, higher pressure near the top. And when there is no change in the winds with height, these parts of the vortex would just tend to move together, moving with the mean winds. Wind shear is when the winds are changing with height. Here I'm just showing the wind speed increasing with height, but you could also have the direction changing. And because the vortex tends to move with the mean winds, in a storm like this, you might have the low level vortex moving slowly, the upper level vortex is moving more rapidly, the system gets tilted over, and that's very unfavorable for development, and it often can be a hurricane killer. So let me just show this satellite image. This is an image of a highly sheared storm. Down here, you're seeing the low level clouds. Over here are the high clouds. It looks kind of diffused, and that's because it's a lot of ice crystals at upper levels compared to the liquid water at low levels. And the upper level vortex is kind of hidden within this area of high clouds. And because of the shear, that has been moved off well to the east of the storm, and the low level center has been exposed. And what this often means is that dry air has now moved over the center of the storm. And as I mentioned, that leads to evaporation. It's unfavorable for the deep convective clouds that we need to invigorate a storm, and often can weaken these storms. Now, we've seen this sometimes early on in development, and as the shear weakens and the storm starts to realign, that often can be a cause for sudden intensification of storms. That realignment is really critical to the intensification process. And then, as I mentioned before, convective systems and local areas of circulation play a critical role. About 60% of Atlantic tropical cyclones and 85% of major hurricanes form from African disturbances. These disturbances typically form over the Ethiopian highlands. Those mountains are heated up by daytime heating, so you get this pulsing of convective clouds. these cloud systems gradually move to the west, sort of on the boundary between the Sahara to the north, the Sahel to the south. And when they get out over the ocean, some of these systems get more organized and eventually can form tropical cyclones. This animation is actually showing the birth and evolution of Hurricane Isabel, which, as you know, came through this area in 2003. So it gives you a sense of the evolution of these storms from these early disturbances over Africa, their movement all the way across the Atlantic, and then eventually landfall somewhere in the U.S. So let's talk a little bit now about what drives rapid intensity change and what that really looks like. So what you see in these plots here are time series of the maximum wind speed within Hurricane Wilma from 2005 and the trend in sea level pressure within the storm. So, obviously as a storm, and I've kind of showed the different categories here on the Saffir-Simpson scale. So early storms are tropical storms that gradually get stronger. And then as they strengthen, they go through these different categories of intensity. Hurricane Wilma, in just a 24-hour period, indicated by these vertical lines, went from a tropical storm with winds of about 50 knots to a Category 5 storm with winds of about 135 knots in just 24 hours. This was actually a record for the Atlantic in terms of rapid intensification. Usually we think of rapid intensification as being 30 knots in 24 hours, and this case was about 90 knots in 24 hours. So an exceptional rate of increase. The sea level pressure is just a measure of the weight of the atmosphere above the surface. In terms, we often refer to these in millibars or hectopascals. A typical surface pressure is about 1,000 millibars. And in Hurricane Wilma, by the time you get to the maximum intensity of the storm, it's at about 880. So you lost about more than 10% of the Earth's mass above the center of the storm. This animation will show the sea surface temperatures by these warmer colors, and I'm going to show you the evolution of Hurricane Wilma. It's a very fascinating cloud evolution. So you can see these rotating cloud bands. You get the initial formation of a small eye, and then it undergoes a reconfiguration and develops this really large eye structure. So it underwent what we call an eye wall replacement cycle, which is pretty typical of major hurricanes. I often ask people when they watch this video, when do you think the maximum intensity of the storm occurred? And they usually say it's at this time when the storm has this monstrous eye. It looks like a fearsome hurricane at that point. You can see in the shading here where the ocean temperatures actually cooled off because of the strong winds in the hurricane. But the maximum intensity, if I can get this playing again, shoot, let me see if I can get it to go, actually occurs when it forms this pinhole eye with a much smaller storm. And that corresponds to this time. And then it went through an eye wall replacement cycle, which weakened the storm initially, and it never really recovered after that. It kind of stayed the same intensity until it moved off toward Florida. So Wilma was important because it had the very warm ocean temperatures. It had a low wind shear environment. It had moist air. And of course, once you have those conditions, it's very easy to maintain the very strong thunderstorms that cause it to intensify. So, of course, NASA works on developing a range of technologies that measure different aspects of the atmosphere and the surface from space. We measure clouds, rainfall, sea surface temperature, humidity, air temperature, winds, and lightning. I'll primarily focus on clouds, rainfall, and sea surface temperature. I already showed you one example of the moisture or humidity. We do have satellites that measure temperature and humidity in the environment, which is very useful. Winds is much more challenging. We can estimate winds from the motion of clouds. We have some sensors that can look at surface winds over the ocean by how rough the ocean surface is caused by stronger winds, but it still remains one of, I think, our biggest challenges in terms of measurements from space. With the latest series of geostationary satellites from NOAA, the GOES satellites, we now have lightning mappers as part of those missions. So now we can watch the continuous development of lightning with these systems, and that can tell us something about the strength of the convection within these storms. But I'm going to focus on the first three of these observables for the most part. And let's start with clouds here. So on the left is one of the first images of a hurricane from space from the TIROS-3 satellite in 1961. This is Hurricane Anna. You can see how grainy that image is. And frankly, if you didn't know that that was a hurricane, you might not guess that it was. It doesn't have a clear eye. It's just a saturated image that shows you there's a big cloud system, but that's about it. On the right, though, is what the type of data that we can get from this latest generation of GOES satellites. GOES is the geostationary operational environmental satellites that are run by NOAA. The latest series has advances that give us near true color imagery, very high temporal resolution. So we're getting images now every 5 to 10 minutes, whereas it used to be only every 15 to 30. Actually, the previous series, I think, was 30 minutes to an hour apart. So we're getting much more frequent observations, much higher resolution, and much better quality. So in this example here, I think this is Hurricane Harvey from 2017. What you're seeing now is the visible imagery during the day. So you're just seeing the reflected sunlight at the top of the clouds, and you'll kind of see the shading with during the night. And then at the end of this loop, let me just jump to it, you'll see the transition to night. And there you're measuring the infrared emission from the cloud. So we're measuring temperatures at cloud top, and that tells us something about how deep those clouds are. So that's the latest technology we have from an operational perspective. Now, this data is useful in being able to track the clouds, but the disadvantage is that you're primarily seeing cloud top only. And a lot of the times we want to know what's happening underneath the cloud. So in this case, you can kind of guess where the center is. You might guess that it's sort of in this area at the center of the spiral. This kind of might look like an eye, but it's actually a shadow, I believe, from a deep convection here on the west side of the storm. But it really doesn't tell you a lot about what's happening underneath. So again, this is visible imagery. At night, we have measurements in the infrared, but we also have sensors that can measure in the microwave spectrum. And there's a couple different approaches for that. One is a passive measurement. So the Earth's atmosphere and the surface are emitting energy in the microwave spectrum. Clouds actually, or precipitation can emit microwave energy at a different temperature than you see in the environment. And then ice particles higher up in the storm tend to scatter that energy, and it drops the measured temperature. And so we can use those signals to get an estimate of where precipitation occurs. So here's an example showing you what we call brightness temperatures from a microwave instrument, where these temperatures indicate where precipitation is occurring. So it's basically giving you an X-ray of the storm. So if you remember from this image, I mentioned how this area of high cloud tops is producing a shadow. That's an area of intense convection, and that's where we see temperatures that are consistent with very heavy rainfall on the western side of the eye wall. The center of the storm is in the middle of this precipitation ring, and then we have these outer rain bands that occur. So this type of data is very useful for tracking the evolution of the precipitation structure. And as I'll show in a moment, it allows us to track precipitation with these storms globally, and even do precipitation accumulation to look at just how much rainfall a storm produces over its life cycle. Now, another way to use microwave energy to measure precipitation is active microwave sensors. This is the basis of radar. So a radar transmits out a microwave pulse, and then it measures how much of that pulse gets scattered back to the sensor And that's usually tied to how large the drops and how many drops of precipitation or cloud are within the cloud system. This is data from the Global Precipitation Measurement Mission. It has a microwave imager, which is the wider swath of rainfall, provides the rainfall data that you see uh, shown at the surface. And then this three-dimensional view is coming from a radar. So it basically is like giving a CAT scan of the storm compared to the X-ray. So the center of the storm is right in here. You're seeing the upper levels of the eye wall. Where you see these warmer colors is the liquid layer, and the blue represents the ice layer. Because the temperature is decreasing with height, that precipitation eventually transitions from liquid to ice, and then as it falls to the surface, it then melts and becomes liquid again. Here it's just kind of scanning down through the storm and back up. You can see this deeper convection near the center. You can kind of sense the um, structure of the outer rain bands in this storm. So it gives a very complementary view. And the radar is providing one of our more accurate measures of rainfall from space. The microwave sensors are good, but they're not as accurate as the radar is. And GPM is probably our best satellite for measuring precipitation. The radiometer that it has, the passive measurements are the most accurate of any that are in space. But we can use it as a reference to look at data from other sensors that form a constellation of precipitation measuring sensors. And GPM helps us to construct these maps of precipitation nowadays every 30 minutes at about a tenth of a degree resolution. It allows us to track the evolution of precipitation, so you can see storms here forming tropical storms, other just general convective systems in the tropics. We've got mid-latitude systems that we can track. So this has been a very valuable data set. We had an earlier mission called the Tropical Rainfall Measurement Mission, which had the first radar in space starting in 1997. It launched. GPM launched in 2014 and is still going. TRIM ended back in 2015 or so. But it's been a very useful satellite for collecting an extensive amount of information on precipitation structure within tropical cyclones. Within a short time, these satellites could produce more information on rainfall within tropical cyclones than many years of aircraft measurements, because you can sample things globally, whereas aircraft measurements tend to be concentrated just in the Western Atlantic and the Caribbean region. Now we'll move to sea surface temperatures. I like to show this animation. It's from the 2005 season. And what you're seeing is sea surface temperature with temperatures warmer than 26 degrees Celsius indicated in orange. So those are the temperatures that are warm enough to support tropical cyclone growth. The blue indicates colder temperatures. And then you're seeing the cloud imagery that reflects different systems. And as the season goes on here, you'll see different storms. Let me just get a quick drink of water. So you'll see different cloud systems eventually spinning up in the storms. Here goes Brett. And then I think the next one was, if I remember right, Cindy. Yeah, there it is. And then Dennis was the first major storm that season. And you'll see as it moves into the Caribbean, where the strong winds actually cool off the ocean temperatures, and it takes days for those ocean temperatures to recover. So if you get cooling like that, and then another storm follows in the wake of that storm, the cold water associated with the previous storm can actually influence the intensification of the subsequent storm. But it has to be within several days, otherwise the ocean typically recovers. Now, on the periphery of these warm waters, you'll get more rapid cooling because the warm water is pretty shallow. In these other areas, it tends to be deeper. Now, there's Irene. I want you to follow this cloud system here. It's a system that's struggling to really do anything. But as it gets closer to these very warm waters, you'll see it becomes Hurricane Katrina. And then as it gets over the Gulf and intensifies, you get that cooling of the ocean. So we're able to track these systems. Many times, like with Katrina, they struggle and then they hit this window where they get ideal conditions. The wind shear drops, the ocean temperatures are maximum, the humidity environment is good, and they can suddenly go. And those are the situations that cause the most trouble for forecasters. And these types of observations are really critical then to looking at how these storms evolve. Now, we use a variety of satellite data to get estimates of the ocean temperatures. There are infrared instruments that do this. There are microwave instruments that also, at certain frequencies, give us ocean temperatures. And we've had ocean temperatures going back for many decades now. And often at the beginning of the hurricane season, we are looking at how the ocean temperatures differ from the long-term average. These are called sea surface temperature anomalies. So here you're seeing in the warmer colors are temperatures above normal versus in the blue below normal. This is for last September, so in the middle of the last hurricane season. You'll notice these cold temperatures along the equator. This was as the current La Nina was just getting going. The previous year, you would have seen warm temperatures in that region associated with La Nina. You'll see areas of very warm temperatures at mid latitudes in the Pacific and here in the Atlantic, and also at very high latitudes. We've seen this every summer now for many years, these very high ocean temperatures. And one might suspect that these are pretty persistent features in the ocean, and I believe sometimes these features can also influence long-term seasonal weather. And in fact, I wouldn't be surprised if studies come out later suggesting that this warm anomaly in the Pacific actually played a role in a lot of our winter weather and even the fires, creating the condition for the fires in California earlier this year. At this time last year, the ocean temperatures in the tropical Atlantic and Eastern Pacific were anywhere from 1 to maybe 3 degrees warmer than normal. So, and that's been pretty typical of hurricane seasons over the last decade or two. And that's one of the reasons why we've been seeing heightened hurricane activity since about the early 90s. So now I want to shift to some of the airborne measurements that we've taken over the years. I've listed a number of campaigns that we've done. I won't try to spell out all the acronyms here. We're with government. We love acronyms. But we've done a number of campaigns over the years. I've been involved in many of these. I co-led a 2010 campaign called the Genesis and Rapid Intensification Processes campaign, which I'll show an animation of at the moment. And then I was the PI for a 3-year mission using unmanned aircraft to fly over hurricanes. And I'll show something from that as well. So one of our main aircraft that we've used for hurricane flights over the years has been a DC-8 aircraft that was recently retired, unfortunately, but it was one that could penetrate storms. I did multiple flights through hurricanes on that aircraft. And in 2010, it was also the first year we used an unmanned Global Hawk aircraft. And you'll see a picture of that in a moment. But that's one of the larger drone aircraft. We got those from Northrop Grumman back in the late 2000s. We modified it to handle scientific payloads and had to update the flight systems to work for us because DoD took their own software. And the advantage of that aircraft is it could fly for 24 hours or more. So in this animation, this is from a storm that we flew in 2010 with multiple aircraft, NOAA, Air Force, and NASA aircraft. The Global Hawk was based in California, so it's coming out here. And you'll see all these aircraft converge on Hurricane Carl at the same time. So I think there were 2 or 3 NASA aircraft, 3 maybe NOAA aircraft, and repeated cycles of the Air Force C-130s. So the manned aircraft can only stay out there for maybe 6 hours at most, with an hour or 2 of ferrying time. The Global Hawk, again, could stay out there for a very long time, even coming all the way from California. The C-130 that you're seeing here, right there in the blue aircraft, was actually the second one on station during that time. The first one had already gone home, and now it's gone home, and you'll see the Global Hawk keeps on going. I think overall we did about 14 hours over the storm with the Global Hawk, with about 5 hours of transit both ways to and from California. So that this is probably one of the most heavily observed storms ever, and it was a result of our partnering with NOAA in these campaigns to maximize the data collection. So it's very valuable. NASA does these field campaigns because it provides numerous opportunities for us for different activities. We use it to collect observations that can calibrate or validate satellite sensors. So we have certain types of instruments in space, and we use like instruments on the aircraft so we can compare the measurements directly. It's also a way for us to evaluate new sensor concepts that someday could be in space. And it's also a way for us to conduct what we call process studies, to collect observations to help us to better understand how hurricanes work. So next I will show, this is a video from the Hurricane and Severe Storm Sentinel mission that I led for multiple years. This is the Global Hawk. It has a wingspan of about 116 feet, and the fuselage is about 43 feet long. This is a view from a camera underneath on the belly of the aircraft. We typically did our flights from the Waltz Flight Facility out near the Eastern Shore. And this is our operations center. We had pilots up in the front room, our scientists and instrument folks in the back room. Overall, we did a large number of hours, 21 flights over 9 named storms. This will show you the different storms. We typically took off in the morning one day and returned the next day. So there I am in the operations center. The person next to me was my project manager and also our payload manager. And we would set waypoints for the aircraft to fly. We would sometimes modify that during flight as the storm behavior dictated making changes. This shows some of the instruments being integrated into the aircraft. We had a couple of remote sensors, laser-based and radar-based. These are dropsondes that are released from the aircraft that give us profiles of temperature, humidity, and winds as they fall to the surface. You'll see it shoot out the back here in just a moment. There it goes. A little parachute comes out so it can fall slowly. That's Marilyn Vasquez, my project manager. Deanna Hintz, who was my postdoc at the time, and one of the images coming up will even show my PhD advisor there who came out to the field. So we'd be in the operations center for 24 hours. We'd break it up into 3 8-hour shifts. And then outside our shifts, we'd have to do our day job. We had to keep up with email and do planning for the next day. One of the things that we were looking at was how the Saharan air layer interacted with storms. This was a very dry, dusty air mass that is thought to influence storm development. And this is just an example of data collected in one of the storms, showing the laser data that measured clouds and aerosols, and the dropsonde data is each of those little colored vertical profiles. So gives you a sense of what we can collect. This is a low light camera at night. Right at the beginning, it showed an overpass over the eye. Every year after the campaign, we'd have a science team meeting where we brought everybody together. We'd talk about the past campaign. We'd plan for the future. We'd examine scientific results. And it was a way for people to develop collaborations as well. So it was, we did that on an annual basis. So let me move on from that, just kind of continues on. So now let's kind of look toward the future. How will a warming climate impact hurricanes? And we'll focus on a couple different things that I think we have the most knowledge about here, which is going back to these basic ingredients: warm ocean temperatures and high humidity. Those are things that we know fairly confidently how they will change in a future climate. Vertical wind shear changes are more variable and less well understood. And so it introduces a lot more uncertainty into the projections. But, all other things set aside, warming ocean temperatures and warming air should lead to stronger storms because there's more energy. The area of warm water expands, so there's a broader area over which storms could form. So we would think that we'd get more storms and more intense storms. So is that the case? So this is just showing you the animation sometimes works and sometimes doesn't. Let me try it again. There we go. So this is just showing the global surface temperature trends since 1880. This is a reconstruction using observations and models over a long period of time. And you can see how things are gradually warming up through about 1980, and then you get a much more rapid warming after that. This is the sort of the hockey stick thing that you often see, and you'll see by the end of this period just how warm the Earth, how much the Earth is warming, particularly over land, but also over the ocean. So the air temperature is warming quite a bit, and the ocean temperatures are warming substantially. So um, what that means, one, with the warmer oceans, you got more energy, so the maximum potential energy of the storm can be greater. But also, warmer air can hold more water vapor. And in fact, for about every 1 degree Celsius increase in temperature, the air can hold about 7% more water vapor. So we generally expect that warmer air will lead to more available moisture, which will lead to more precipitation. So storms will get wetter, and because of the warming, they'll also likely become stronger. In theory, all of the things neglected at this point. So let's take a look at some of the projections. So there was a very thorough study done by a number of authors looking at observations and uh, model projections. And this is a summary of those model projections looking at a total warming of about 2 degrees Celsius. Right now, we are over 1 degree Celsius, approaching, I think, 1.5. And we expect to reach 2 degrees Celsius sometime later in this century. Let's focus on this plot in the lower right. This is global. You can see how this plot will differ for different ocean basins. But let me explain what you're seeing here. So this is showing the anticipated, the percent change in different characteristics by the end. I think this is by the end of the century. So it's showing the change in tropical cyclone frequency. So all storms from tropical storms up to major hurricanes, the change in category 4 to 5 storms, the change in the average intensity of the storm, and the average rainfall rate. The dark blue line shows the median value. So if you take all of the different estimates and you take the value that's right at the middle, that's the median. And the blue box shows you the range of the estimates. So when this blue box has a large vertical extent, that means there's a lot of uncertainty in the projections. And if we look at, say, tropical cyclone frequency, you see that the median actually is negative. It suggests that potentially we can see globally a decrease in the frequency of all storms, and maybe a slight decrease in the frequency of the very intense storms. But again, there's a lot of uncertainty. Some models increase the frequency, others decrease it. So it's less certain how those things are going to change. But if you look at the average intensity and the average rainfall, they're both going to increase. All models show that they're going to increase. It's just a matter of how much. So if you look at the median, that's an average increase of, or median increase of about 5%. So if you've got a 100 knot, a storm, average intensity of 100 knots, it's going to go up to 105. May seem small, but that's over all of the storms, and that usually is going to be reflected in some cases becoming more extreme. What you'll see for rainfall is a significant increase in the rainfall. The median increase is about 14%. Remember, this is 2 degrees Celsius warming, and I said that for every 1 degree Celsius, you get about 7% more moisture. So that's consistent with just the fact that warm air can hold more water, and so we get wetter storms. And over the last many years, we've seen a number of major rainfall events. Helene or Helene, I'm not sure how most people pronounce it. Helene, Helene, it depends on what language, I guess. um, it produced extreme rainfall, partly because of the effects of the warming of the air, but partly also because right before landfall of Helene, you had what we call predecessor rain events. Far to the north of the storm, there was already heavy rainfall occurring that was being exacerbated by lifting of air over the mountains. And so it was already saturated by the time the storm even made landfall. And these projections suggest that these types of events could become worse in the future. So just to finish up here, NASA uses the vantage point of space to provide a lot of essential data to help us understand storms. The information is valuable both for scientific research, but also it feeds in often to operational forecasting and a variety of other applications. And we also do a lot of airborne work. We haven't done as much lately for various reasons, but that is often critical in helping us to prepare for future missions. So I'll stop there. I think I probably ran a bit long. I'm happy to stay around as long as you want to answer questions, and I'll stop there.
Thank you, Scott, so much. If you can unshare, we'll come back and
figure out how to do that. Here it is. Okay.
Let me put a spotlight on for everyone. Oh, I put the spotlight not on Scott, but on Joe. So that's not on. Joe, I don't need a spotlight on you.
I didn't know you had that background.
Okay, here we go. All right. Well, thank you so much. That was amazing, the information that we're able to gather. And I'll start off. I'm from New Orleans. My family is still there. And so hurricanes have always grew up with them. We had hurricane days, not snow days at school. I'll just put that out there. So it's very important and personal to me for having lived through Katrina and I you almost forget how many storms were in that 2005 series, that even after Katrina there was Rita, and you just kind of forget all of that.
Well, and don't forget we got all the way into the Greek letters for the first time.
Yeah. So how was it? How was it like flying into the middle of a hurricane, just on a personal experience level?
Well, fortunately, on the DC-8 aircraft, it wasn't that bad. So in hurricanes, there's not a lot. Wind shear is the main cause of turbulence a lot of the times, and most of the strong wind shear within a hurricane is down low, because you get the maximum winds near the surface, and then they drop off really quickly with height. And so that's where it gets really turbulent. And the NOAA and Air Force aircraft fly down there, and it can get pretty rough. On the DC-8, we were flying up around 38,000 feet, and the pilots did everything they can to. They had a radar on the aircraft that could see where the thunderstorms were, and they would kind of go around the worst of it. So it really wasn't too bad for us. Probably no worse than like a somewhat rough flight on a commercial flight. And we did repeated flights. One of the best ones for me was Hurricane Earl in 2010, where the first day we flew the storm when it went from a Category 1 to a Category 2 storm. And the second day it went from a Category 3 to a Category 4. And most of the time, looking out the window, things were clouded over. So I wasn't really getting that really nice stadium effect that I had wanted. And the pilots were about ready to leave, but I managed to get them to do one last flight or pass through. And on that last pass, it finally had blue sky up above. You could look down to the ocean surface and see the swirl of clouds. And that was pretty phenomenal. And I remember landing on the ground and talking to this guy who had been doing flights for almost 50 years. And here I was getting that experience. And he said for all his flights over 50 years, he had never seen a clear eye. So it's a rare thing to experience. It's a bit of an adventure. You take precautions, but overall wasn't too bad. I haven't done one of the NOAA P3 flights. I flew on their aircraft in winter storms, but not so much a hurricane.
Very cool. Well, being in the eye, I mean, is a surreal experience even on land. So when it comes through after all of that, I can't imagine flying through that.
I'd much
Are
rather
there
do it from an aircraft than on land.
are there this might sound I know that there are no stupid questions, but are there hurricanes on other planets that we have seen? Is that or I know that there's storms and things. There's that are
They're
there
different
similar?
phenomena. So I don't know, not sure we've observed what we might consider a hurricane. We've seen areas of circulation that are definitely rotating fluids on a planet. That's probably pretty common to see on a gas planet. Um, but I don't know that we can say, do they qualify as hurricanes? Not really sure.
Okay, so this is an Earth phenomenon. All right. Do we have any questions from the peanut gallery up here? Raise your hand or put it in the chat box, and I can call on you. Don't be shy.
I
Oh,
see.
Alan, go ahead.
Hi, thanks. I got several questions.
Sure.
I'll ask my softball question first, but coming my standard question, which is just how did you get interested in this?
Oh, that's a story. So I started in college as an accounting major, and first semester signed up for classes over the phone. Didn't get all the classes I wanted, so I got into the gym. And I'm an introvert. I don't like crowds. I go into the gym, signed up for a couple classes, needed one more, and I look. I just wanted to get out of there, so I look around the gym. I see this one table that had two signs on it. One said geology, the other said meteorology. There was one person at the geology line, nobody at meteorology. So I went and signed up for the meteorology class. Um, and then I had a professor there whose idea of vacation was to go to Oklahoma to chase tornadoes. So I kind of caught the storm bug from him. And I grew up in the Bay Area. I went to San Francisco State, and we didn't really get much in the way of thunderstorms there. Occasionally, cloud to cloud lightning, but nothing exciting. But that fall, we had some storms move off. Either moved up from the Southern California or off the Sierras, and we had in the middle of the night constant cloud to ground lightning. And it was middle of the night. I stayed up watching it. I just was thrilled by it. So that I kind of got hooked that way.
That's
Total
great.
fluke.
In my fantasy, I'm going to say, well, in that alternate universe, if you had gone to the other table, you still could have been talking to us tonight about geology.
That's true.
My other question is right now, is it like the peak of the storm season in the Southern Hemisphere?
Yeah. So that they're, in their summer, yeah, this March would be sort of the peak of it. In fact, I don't usually follow what's happening down south. I think I did hear something of a storm. Was it in the New Zealand area? I can't remember. But typically around Australia is a frequent place that we see these storms. Sometimes in the South Indian Ocean, like you'll see them approaching Madagascar and hit parts of Africa. They're generally less frequent down there, but they do occur this season. So yeah.
The last question. I'm just also kind of a airplane fanatic all my life. I never did anything related to it except be obsessed with it. So can almost any plane fly into that kind of stuff? I mean, I was surprised to see a DC-8 in there. So that was just, kind of impressive that you could fly that kind of a jet in there.
A larger jet, usually you can. They're pretty hardy, particularly the older ones. As I mentioned, the G4 aircraft is not intended to fly through severe weather. Even at their higher altitude, they will not fly into the worst part of the storm. Um, we replaced the DC-8 with a 777. We're getting that ready for a future science campaign starting in 2027. I still have some questions as to what they can do with that, and whether it can fly into these storms. As you go from all metal aircraft to composite structures, I'm curious as to what you can do.
Yeah, what if you get struck by lightning?
So that's something that we have to see. A lot of the aircraft, some of the other aircraft we use are high altitude aircraft. We have an ER2, which is like a U2 spy plane that can fly up at as high as 70,000 feet. And we tend to put um, sensors on that, and flying from above the storms, it acts like our own little satellite that we can take a lot of measurements looking down. That generally is safe, and we've done the Global Hawk that way too. It would fly up above the storms. But we had one time in 2005 over Hurricane Emily where the ER2 was flying over the storm. It looked fairly normal, but the pilot said that as he flew over it, he encountered really rough conditions, almost to the point of stalling the aircraft. It has a very limited um, zone where it can operate without stalling, and he was pretty close. So eventually he switched from flying over to just flying boxes around it. And after that, they got super cautious with the Air 2 and with the Global Hawks. And it took a long time to convince them that that case was really more of a fluke. And it just happened that at the time he flew over it, there was a strong burst of convection that on the radar looked like a major hailstorm that you'd see over the US. We don't typically see strong hail in a tropical cyclone. So it was a very unique event. It occurred near the maximum intensity, which is also where you don't tend to see strong convection, because by then the temperatures in the atmosphere have adjusted so that there's not a lot of convective instability. The flow is what we kind of call moist neutral. It's not as strong, but it's steady. And so it was just a very fascinating case to see a hailstorm occur in that situation in the eye wall. And I don't think we ever really came up with a good explanation for what happened in that case.
Thanks so much. Appreciate it.
Go ahead,
I have a question, more of a general question as a scientist. Based on the current conditions that you are working under, do you feel scientists will now have to go ahead and limit their research or limit their publications, or be forced not to study something based on the scientific data that your satellites and instrumentation and your research leads you on?
I'm not quite sure I'm getting it. I mean, the data that there's nothing in regarding the data that would limit anybody's ability to research any topic associated with tropical cyclones. There may be non-scientific reasons why people might be limited in what they can study, and the resources that are made available for doing that. I won't get into the reasons, you probably know.
Mhm. Okay, thank you.
Sure.
Just tagging on to that in where we won't talk. I have to say that one last video you showed with the warming from 1800s, I mean, most compelling. And if someone that's not a scientist can't understand that, just not quite sure what they're missing.
Well, typically what you hear is that they don't believe the data. And if someone doesn't want to believe data, what can you do?
Well, I want to ask the question, the chart that you showed earlier where you had the deviation from the norm. Could you tell us again how the zero norm was developed?
So the average condition. So we've been getting ocean temperature estimates from space, say since the 70s, and then prior to that, there are ship records, buoy records, and things like that, where you can kind of reconstruct the earlier temperatures. And so one can take the data over multiple decades to come up with the average, and and that's a spatial, that's an average over time only. So you get the long-term average as a function of latitude and longitude. And so you can take any instantaneous measure of sea surface temperature, remove that average, and that gives you your anomaly. And what we've seen, I mean, this goes back for a good while here, is in the summer, that image I showed where you saw a lot of orange all over the ocean. That's been pretty typical all year round. You'll see some areas where you can get those colder areas, certainly along the equator. That's associated with the El Nino Southern Oscillation. At mid latitudes, that can often be driven by large scale weather patterns that might lead to cooling in some areas, warming in others. Um, but by and large, just like with the surface air temperatures, the oceans have been warming, and particularly warming at middle and higher latitudes, but also plenty in the tropics to make hurricane seasons worse. You know, we used to see a lot of variability in tropical cyclone activity over multiple decades. We called it a multi-decadal cycle. So back in the 20, I think it was in the 30s up until maybe the early 60s was a pretty active period. And then from the 60s until about the mid 90s, it was pretty quiet. You'd only have, less than a dozen storms in a year, in a busy year during those times. And then starting around 1995, we thought we were getting into another active multi-decadal cycle, except here we are now 30 years later, and it hasn't shifted back to inactive. And that's because the ocean temperatures have remained warm. So whatever cycle we might have had before now is being affected by the long-term trend, which seems to be keeping us in a period of enhanced tropical cyclone activity.
And are the warming temperatures decreasing the wind shear potential?
So that's a complicated question because there are winners and losers. On average, there are some areas where it increases, some areas where it decreases, and that is thought to be why we might see fewer storms in the future. That in general, wind shear might be increasing in key areas where tropical cyclones form, so it suppresses the number, but it's not a continuous thing. So you'll have periods where the shear weakens as large scale wave systems move around. And during that period, when the shear weakens, you open up a window for rapid intensification to occur. So even if the total number of storms is lower, the average intensity is increasing because a lot of these storms at some point in their life cycle get that opportunity to intensify. And so on average, they're increasing, even if the numbers aren't necessarily showing a dramatic change. But of course, as I showed, there are large error bars on those trends.
And we started off by saying how many hurricanes have hit Maryland since the 1850s. Are any of the changes in the temperature of the oceans changing the directions of hurricanes in terms of are we the Atlantic going to get more because of the more warmth that's up there?
There have been some studies that have suggested shifts in where storms may occur. I don't know if there's as clear a picture about whether we'll get more landfalls or not at this point. Um, I think what we're seeing is storms being able to form at higher latitudes than what they used to be able to do because the area of sufficiently warm water is expanding. I think the latitude at which storms are reaching their maximum intensity is increasing somewhat, again, because that available warmth is there for up to higher latitudes than before. I've seen some studies that have suggested significant shifts, say in the Western Pacific. I'm not familiar enough with the Atlantic studies to know if there's been a definitive pattern in shifts in the Atlantic. I don't think that's as clear. I mean, we had periods of, frequent landfalls along the U.S. coast to periods where a lot of them were staying offshore and turning northward, off the East Coast instead of making landfall. Whether that might shift back toward landfall, it's kind of difficult to say, I think, at this point.
Well, that's why we need to keep studying it, to keep learning more information and keep gathering the data and creating the sensors and doing all the stuff that you've been doing and your colleagues have been doing to help us understand and hopefully have the understanding well in time to prepare for the impacts if they come. So if there are any other questions tonight?
Oh, I just want to end it on a light note. I'm interested to know what the data meteorologists think of the Jim Cantoris of the world. Or all I know is if Jim Cantoris shows up in your town, it's not a good thing.
Yeah, I met Jim Cantori. He came out to Wallops one time when we were flying the Global Hawks, and he did a whole story on it. And much to our chagrin, he kind of talked about how much each of those drop zones cost. They're kind of expensive, and I shouldn't have told him what they cost. Nice guy, but yeah, you probably don't want him showing up in our neighborhood, in your neighborhood. As for those types of broadcasters, I cringe a lot when I watch that. Most of them try to take precautions. I just fear the day when a road sign detaches from its post and hits one of them and does significant injury. So I don't know. It seems inevitable. Just like we've seen loss of life occasionally by tornado chasers. It just seems like as people, especially now in the YouTube age, you'll see people trying to get out into storms to film it and things like that. Sooner or later, somebody's going to make a mistake. And yeah, I worry about that.
Yeah, they've had their close calls already, and I've seen some. They're just, I asked myself the same thing. What kind of model are you setting for the viewers?
Usually they try to get sort of behind a building so that the winds are behind them. But if they're standing out in those strong winds, there's every possibility of something flying in the air.
All right. Well, on behalf of the Natural History Society of Maryland, let me thank you for sharing your time and your expertise and your knowledge with us and helping us understand our natural world and the phenomenon of our Earth better. And everybody, thank you for joining us. Stay well, stay curious, and hopefully we keep on the lookout for strange meteorologists showing up in your neighborhood.
Maybe we'll see you at the Gem and Mineral Show in what is it, a week or so?
See you at the Gem and Mineral Show in Montgomery County. All right, everybody, take care. Thank you.
All right, thanks for having me.
I have a quick question. I missed the first half of it because I was at work, and I saw that it was recorded. Is it going to be mailed out?
Yeah, it'll be available on the YouTube channel, which is Maryland Nature, in a little bit.
Oh, so I go to the YouTube channel.
Yes, and just if you subscribe to the YouTube channel, you'll be able to get it.
And what's the name of the YouTube channel again? I'm sorry.
I'm sorry. It's Maryland Nature, all spelled out. So Maryland, and then yep.
All right. Thank you very much.
Okay. Take care. Bye.